So hello everyone. We are going to be looking into quantum physics second half. Okay. So what and all are we looking into? So we have learnt about basic motivation behind going for quantum theory because there were many principles in physics that were not able to be solved by classical physics, right? So something like we had various properties to prove in terms of the quantum world, right? So we learned about wave particle duality, we learned about matter waves, we learned about de Broglie stuff, we also learned about Heisenberg's uncertainty, right? How Wien's displacement law and Rayleigh-Jean's law are merged together to give a proper universal formula for energy density and all that we looked upon. Yes. Now we are going to take a look at Ureim show. It is not moving. Just give me a second. Mhm. Yeah. We are going to look at the simple wave equations. How do you represent a wave function, and why do you need a wave function in the first place? And how can you apply wave functions into stuff like particle in 1D and 3D? And what is degeneracy? How do you make the term for the quantum mechanical equivalent of COME, conservation of mechanical energy. Yes. And how do you make the energy formula as well? And then we learn about few theoretical stuff like quantum free electron theory and all that. And finally, we derive density of states, Fermi Dirac statistics. And from the density of states, how do you derive free electron concentration? And as a continuation of free electron concentration itself, we'll start intrinsic semiconductors and do some derivations on that. So if this is clear, we can move on. Yeah. I'm not able to scroll through. Just give me a second. Yes, so we were here, right? So we were deriving an energy formula, and we were also seeing which dominates when based on the distances comparison. And we also saw phase group velocities, and then we are here, right? So there's a very simple way of understanding waves in itself. Yes. So we've learned waves in 11th standard, 12th standard, right? What is a general way of representing a wave? It is amplitude into omega t minus kx, right? But when it comes to quantum world, something that is not very realistically visible, right? How do you associate such an equation, right? So it will obviously have an amplitude. Yes, it will have an angular frequency omega. It will have time t. It will have angular wave number k. It will have distance x. Beautiful. But it will also have a few other parameters, and we'll be looking onto why this e power comes as well. Okay, but in general, as of now, just understand that omega, the wave function is represented as psi of x comma t. This is pronounced as psi. Yes, so that is a e power minus iota times omega t minus kx. Yes, minus iota, again, all that is conventional. Okay, none of us to question. So omega t minus kx. What is omega? Omega is just 2 pi nu. And what is k? K is just 2 pi by lambda. So why don't we take 2 pi common? That's what they've done, right? So a power minus iota 2 pi omega nu t minus x by lambda. Beautiful. Yes. We have a weird habit, right, in quantum physics entirely. What is that weird habit? Planck. We are not going to leave that guy, no? That guy is the one who started all these guys. So we are going to take that guy common. Out of whom I want to put h bar somewhere, right? I would not sleep if I don't put that. So what I'll do is I'll somehow try to take h common out of these guys. Yes. How do I take new length h? Very simple. It is what? E is equal to h nu. Yes. I mean, in turn, it is not about bringing h. It's about bringing the meaningful aspects of defining a wave function. And meaningful aspect of defining a wave function is its energy and its momentum, right? Those are meaningful aspects. That's why you try to bring them into the formula. Yes. So nu is E by h, beautiful. Then what is 1 by lambda? We know that P is equal to h by lambda. So 1 by lambda would be P by h. So we can put P by h as well. So we can take 1 by h common. So in that case, it would be what? A e power minus iota 2 pi by h. So our weird habit got solved because we know very well that h by 2 pi is h bar. So 2 pi by h would be 1 by h bar. So A e power minus iota by h cross et minus px. So this is the generalized way of representing a wave function. A e power minus iota by h cross et minus px. Yes. Okay, beautiful. But that is not something that is giving me enough data. That is just telling me E, X, psi. That's it. Yes. Can I get some nice equation? Can I get something like V is equal to UT plus half AT square, something like that, right? That is all in mechanical world, right? I want a similar equation, not the same thing. I want a similar kind of way of defining properties for quantum physics as well. So what do? I play derivatives. Yes. So what do? I'm taking derivative of psi, the first partial derivative of psi. So dou psi by dou x, whatever was the, you know the properties of differentiation, I believe. So whatever was the coefficient of x in e power something, it will come out. E power minus ax differentiation will be just that minus a will come out into e power the same term. Yes. Plus, there's also another concept here. You will separate these guys into psi of x and phi of t. Okay, and here, because you are going to take time dependent case, a time independent Schrodinger's equation case, you will end of the day, even if you differentiate it together or you differentiate it just alone, just a e power ipx by h cross alone, it will give you the same result. It'll give you the same result. Okay, that essentially means time independency. But don't make yourself confused. Just look into this. You are just taking dou psi by dou x is equal to whatever was the psi of x term. Yes. What was the psi of x term? Whatever was the coefficient of x. What was the coefficient of x? Minus I p by h cross. Right. So you take minus I p by h cross into whatever was there, right? So in this case, you had amplitude into the same thing, and there's also another minus here, so plus. Yes. So it will be total IP by h cross into psi. Beautiful. You got dou psi by dou x. But and there's one interpretation here. This will not be part of the proof, but just understand this. So yeah, if I want an expression for momentum itself, right? So momentum in turn is just P, but in quantum world, when you want to define quantities, psi comes in way. Okay, comes together. Yes. So P psi would be what? P psi would be this I by h cross goes that side, right? So h by I, h cross by I, dou psi by dou x would be P psi. So in turn, actually, if you observe this carefully, if I want to know P, right? If I want to know P, what I'll do is I will know what my wave function is, that is psi. What I'll do is I will just try to what? Partially differentiate it with respect to x and multiply it by h by I cross. Sorry, h cross by I. That will give me what? P psi. I can just find the value of P from there. Yes. Essentially, what is it telling me? Take the partial differentiation of x with respect to of pi of phi and then multiply it by h by I, h cross by I. That will give you this. This is essentially the understanding of eigenvalues, eigenvectors, which you'll be learning in your linear algebra course next semester. Okay, that just means that when you have a quantity, you multiply it by a certain vector, that will be equal to the same quantity multiplied by a scalar. Okay, so in this case, you are having a function, right? And you are having a value multiplied by another operator, right? So in this case, you are having a function, same functions, two same functions, a value and an operator. An operator that operates on a function is giving you the same function multiplied by a simple value. Okay, that is what the property of eigen is, which you will be learning next semester properly. Okay, just a glimpse of it. Okay. Now what are you doing? You are trying to differentiate it again. So what will that give you? It will be the same quantity repeating again. So it will be what dou square psi by dou x square is equal to I square p square by h cross square into same psi, right? So I square p square by h cross square into same psi, right? Because it is e power. power ax. Yes. So I square is minus 1. So minus 1. P square by h cross square into psi. What is P square? Very well. P square is what? 2mk. Yes. What is K? Kinetic energy. Kinetic energy is total minus potential. Why am I doing this? Meaningful equation. So that's why. So 2m into E minus V. Substitute it there. So what do you get? You get minus 2m into E minus V by h cross square into psi would be dou square psi by dou x square. Beautiful. Let's try to take, and there was already a minus. There, one sec. Yeah, so what do you have here? You have dou square psi by dou x square is equal to minus p square by h cross square into psi of x. Yes. Now, when you substitute these guys, you will, I think, have an iota somewhere. Okay, no worries. So you take this guy there. What will happen? If you take this guy there, he'll be minus h cross square by 2m, dou square psi by dou x square plus v psi is equal to e psi. How do you do this actually? You will separate these guys. So that it'll become E psi minus V psi, right? And then this h cross square and this 2m will go that side. So it'll be h cross square by 2m. So h cross square by 2m, dou square psi by dou x square is equal to E psi minus V psi. So in that case, E psi is equal to V psi minus h cross square by 2m dou square psi by dou x square. That is it, right? So essentially, for time independent Schrödinger's equation, you have to just arrive at this place. Minus h cross square by 2m dou square psi by dou square plus v psi is equal to e psi. This is the kinetic energy equivalent. This is the potential energy. This is the total energy. So this is the total mechanical, quantum mechanical equivalent of conservation of mechanical energy. Yes. So you can also complicate this if you want. You can try to take all the three dimensions. In that case, it will not just be dou square by dou x square. It will be dou square by dou x square, y square, dou square. They just took psi common if you observe here. Yes. Oh, this is called a Laplacian, Hamiltonian, Laplacian operator, I guess. Yeah, Laplacian operator. So minus h cross square by 2m del square plus v, the whole psi is equal to e psi. Beautiful. This whole thing is called Hamiltonian operator. So h psi is equal to e psi. If you go Google quantum formula, something like that, right? You'll always get kind of these things, right? So h psi is equal to e psi is a very popular equation in quantum physics. So that's what they've derived. Yes. So this is time independent Schrödinger's equation. When you want to do time dependent case, what do? You try to differentiate it with respect to whom? T. Yes. You have to consider the time case as well. So what do? Dou psi by dou t you say, right? When you take t, then what are the coefficients of t? Minus ei by h cross, right? So minus ei by h cross into the same psi will repeat. Yes. Now, what is this? What do I want? I want the same repetition, right? So I want the same time independence Schrödinger's case with time being embedded into that, right? I want to represent time in a way, right? How am I representing? By substituting what? By substituting the total energy. Yes. So E psi, by using the time dependent thing, I'm considering time dependent case and I'm taking E psi. So in that case, minus I by h cross will go that side. So that will become minus h cross by I. Minus h cross by I. What is I? I is minus, what is I? 1 by I. 1 by I would be what? Minus 1, right? Because 1 by I would be I square. I by I square would be minus 1. So already you had minus 1. So minus 1 by I would be what? Simply I. Simply I, right? So it will be I h cross. I'm not able to write it. If I write it, it does not scroll. That's why. Okay. So what happens here? Minus h cross by I, and you multiply and divide it by I. So minus 1 and minus 1 cancels out. You just have high h cross. And then here you have the same thing, dou psi by dou t, and here you have e psi. I'm substituting this e psi in the overall formula. The overall formula is this. Yes, the overall formula is minus h cross square by 2m, the independent formula which we had, dou square psi by dou x square plus v psi is equal to e psi. This is what we had, right? Now you have to just consider time in these cases, right? So psi of x comma t, b of x comma t, psi of x comma t, e of x, e psi will be substituted by whom? He'll be substituted by the equation which we just derived, I h cross something, right? So that will give you the final time dependence Schrödinger's equation. Okay. So minus h cross square by 2m, dou square psi by dou x square plus v psi is equal to I h cross dou psi by dou t. Okay. Are we clear till this point?
Yeah.
Thank you so much. I'm struggling to shift my slides. Okay, fine. Yeah, now it works. Okay, so what happens here? Why is psi important? What is psi essentially? Psi is a wave function. It's a complex function. Obviously, it has iota in it. Yes, and it can. What does it represent? It represents the particles or waves, whatever it is, right? So that particular entity's complete information of that entity, right? In this case, complete information of the state of the particle in motion at any particular given time and location, that is x and t. In this case, time and location is determined by x, y, z, and time is determined by t. Yes, beautiful. What are the key properties? It has to be finite, it has to be single valued, it should have first order derivatives, it should be continuous, it should be square integrable. Square integrable property is this, right? If you integrate it from minus infinity to infinity, basically, what does this thing represent actually? Psi is the actual wave function. Psi star is the conjugate of that wave function. Conjugate is simply a plus iota b. Na a minus iota b is the conjugate of a plus iota b. Yes. So generally, if we will not have that things, so psi and psi star could be same. But in general, according to complex algebra, psi star or z bar would be mod z square. Remember, the same way psi star would be mod psi square. So psi star from minus infinity to infinity represents what? It represents the probability of that wave function existing between minus infinity plus infinity. That is, you are literally searching for the entire universe. Okay. And finding if there is a existence of that thing. What is the answer? One. It has to be existing if in the entire universe, right? So that is what it is. A linear combination would also represent a wave function. It is related to the quantum mechanical particle, and linear operators is basically alpha beta multiplied together, that makes a wave function in turn also. Yes, so summarizing it all, psi in general was represented by a e power minus iota by h cross into et minus px, and we saw for getting eigen for getting the values of p and e, we used eigen operators, right? We used minus h cross, I'm not sure, I think it was this one, right? So it was h by iota dou by dou x. That was the operator when you want to get p, right? And similarly for e, we saw it was I h cross dou by dou t, and time independent was minus h cross square by 2m dou square psi by dou square plus b psi is equal to e psi. The same thing with e psi substituted, and v and putting t also in the parameters makes you time dependent. Yes. Now, one-dimensional potential well is also very simple. I'll quickly go. I'm taking too much time. Yes. So this is simple. An electron is trapped in a infinitely long one-dimensional potential well. This electron can only range between 0 to L, and 0 and L not included. It can only exist between 0 to L, right? In that case, how do you represent the wave function of such a particle? That is the question here. If you observe well here, right, the potential of that function, right, would be infinity in the regions where it is not existing. Right? It is not existing there. Yes, it is restricted to move between this region only. So the potential here and there would be infinity, and the potential would be zero at the path. Right? The potential will be zero at that path. So this is all that we have. This is all that we know and defined. Yes. With just this information, I cannot do anything to derive my wave function. How can I derive it? Yes. To derive it, let's start from our time independence Schrödinger's equation, right? What is that? Minus h cross square by 2m dou square psi by dou x square plus v psi is equal to e psi. Beautiful. Now, you have to somehow take psi out of this. We very well know potential was zero when it was existing, right? In that path. So we can neglect this psi. We can neglect this v itself. Yes. When you neglect this v of x is equal to 0, what do you get? You get this thing. Yes. What do you get? What they've done, they just taken common divided stuff so that they can get an equation in a nice form. I'll show you what kind of nice form it is anyways. Okay. So we had minus h cross square by 2m dou square psi by dou x square plus b psi was 0. So let's just ignore it. Is e psi. Yes. Now let's just take this guy there. So dou square psi by dou x square is equal to 2m by h cross square minus sign and e psi. Yes. Let's take this guy there. Because it is minus sign, now it will become plus sign. Dou square psi by dou x square plus 2m by h cross square into E psi is equal to 0. This is what we end up with. Yes. Why am I doing this in the first place? Because I don't know how to solve an equation. That is the thing. Okay. I don't know how to solve a second order differential equation. Yes. If I don't know how to solve a second order differential equation, what will I do? I will put it in a form in such a way that I will know how to solve it. Basically, I'll put it in a form in such a way that could be a standard form, and using some given information, I'll somehow land up in a way that I can get the solution for it. Yes. So in this case, the whatever equation that is of the form dou square psi by dou x square plus k square psi is equal to 0. Whatever equation of this form corresponds to this equation. So the cos kx. You need not prove anything of the sort. This is implicit. Okay. Yes. Now, given that it is of this form, let's firstly store the values. We'll be using this in a while. Okay. What is k square? K square would be this term, right? According to comparison. So k square is equal to 2m a by h cross square. Beautiful. Now let's try to, we'll use this guy at last. I'm just keeping this guy for future use. Now, all I have is a sin kx plus b cos kx. But I cannot take any meaningful information out of this, right? To get meaningful information, I have to apply some general information that I know. The general information I know is the particle cannot exist at both ends also. It can only exist between. So when x is equal to 0 also, it cannot exist, so psi will be 0. When x is equal to L also, the maximum length, the psi will be 0, right? So first I'll substitute x equals 0. When you substitute x equals 0, what will happen? This will become 0, right? And this will become 0. So in that case, you are getting 0 is equal to 0 plus b cos kx. In that case, you are literally getting cos kx is equal to, the x is also 0. So cos 0 is equal, sorry. I'm mixing up. Yes. So what was the information you had when x equal to 0? This is equal to 0. So in that case, cos kx is equal to 0. So in that case, there was also a b here. B cos kx is equal to 0. But in turn, k cos 0 is 1. So in that case, what is the value of b? The b's value becomes 0 in turn. Yes. So if b becomes 0, don't you think the entire term vanishes off? By just applying one initial condition, I'm arriving at a formula that gives me a replacement of b cos kx with a 0. Yes. So I can easily put what? Psi of x is equal to Peru a sin kx only. A sin kx only. Yes. Beautiful. Now I have a sin kx information. I still don't have what is the information of a, what is the information of k and all that, right? I need to put that also into my meaningful form of representing psi. Yes. So what I do, I try to substitute x equal to L. So when you substitute x equal to L, psi would be 0, right? So a sin x is equal to L. So sin KL. So in this case, sin KL becomes 0. In that case, KL becomes n pi, right? In that case, K becomes n pi by L. So I'm getting a beautiful relation for K. Yes. So I'll substitute it now. After every progressive step, you substitute it, right? So A sin n pi x by L. This is what I'm getting as psi of x. I'm still not satisfied. I'm not getting what the value of A is, right? I have literally used all the information I have. What else can I use? The beautiful property, square integral property. What is that? I search through the entire universe. The probability of finding my wave is 1. Yes. So probability is represented by psi star from minus infinity to plus infinity. This has to be 1. Yes. But I need not do minus infinity plus infinity. I very well know the particle only exists between 0 to L. Right. So let's just put 0 to L here. Yes. I know very well psi is what? A sin n pi x by L, and psi star will also be a n sin n pi x by L. Both are real functions only. Yes. So a square sin square n pi x by L. If you integrate this guy, it should give you 1 from 0 to, yeah. Okay. That is what it is. Now, you very well know the integral of sin square. You cannot directly do it. So sin square theta is equal to what? 1 minus cos 2x by 2. 1 minus cos 2 theta by 2. Yes. So in that case, I would just substitute as 1 minus cos 2 n pi x by L. Yes. Beautiful. and take 1/2 outside, take a square outside. Now just apply the limits. When you put x equal to 0, what happens there? A square by x. So you get what? I think they are missing out on something. Just give me a second. Yeah. So what happens here? A square into 1 minus cos 2x. Cos 2x. In this case, x is n by x by l. Right? And obviously, with respect to n by x by l also, there will be an n by l term here. Yes. Uh, integrating this from 0 to L, right? 0 to L. So this will be what? Substitute L here. If you substitute L here, it will be just L here. If you substitute L here, it will be what? 2n pi L by L. In turn, it is just sine 2n pi. Sine 2n pi is also 0. So in that case, that will vanish off. If you substitute 0, it will be 0. If you substitute 0, it will be 0. Sine 0 is 0. X, if it is 0, it is 0. Yes. Overall, it is giving me what? It is giving me what? 1, right? But there was a prefix here, a square by 2. So in that case, I'm getting what is the expression I'm getting? A square is equal to 2 by L. A is equal to root of 2 over L. So in turn, I'm putting my psi function as what? The psi function was what? A sine n pi x by L. Now A became root of 2 over L sine n pi x by L. And that comes out to be the final derivation of one-dimensional potential wells wave function. This is just psi x, right? If you have many things, right? Psi y, psi z and all, it will be root of 2 by L sine n pi y by L sine n pi y by L. And if it is z, it will be root of 2 over L sine n pi z by L. Yes. So in turn, psi of x is what? Psi of x is psi of and psi of x comma y comma z is psi of x, psi of y, psi of z all multiplied together. It will be just root of 2 by Lx. You can also substitute this as Lx, Ly, Lz for respective terms. But if they're all equal, you can put them as L itself. Yes. So this generalizes to 3D. So in this generalizes to 3D box itself. Okay. So we'll come to energy. Don't worry. So in a 3D box, this is how it should look like. Root of 2 over Lx sine n pi x by L x and so on, so on, so on. Yes. And you can take a Lx, Ly, Lz all equal to L and you will get a similar term like this. Root of 8 by L cube. So all these sign terms will be just there. Yes. And what is energy? Remember, we saved something for future. What was it? We saved k square is equal to 2me by h cross square, if I remember correctly. Yes, this is what we saved. Essentially, also we derived at the same formula that k was equal to what? K was equal to n pi x by L, if I remember correctly. Yes, n pi by L, if I remember correctly. Yes, so n pi by L. So you square it all. So this is equal to 2m e by h cross square. Now, since pi and all is there, I can write h cross square as h square into 4 pi square, right? H by 2 pi, so h cross square 4 pi square. Yes, beautiful. So pi square beautifully cancels out. So essentially, what is the expression you're getting for E? See this. So E would be what? N square h square. This is just h square, not h cross square, right? And then you will have 2 into 4, 8. And then you will have m. And then you will have L square. Okay. So essentially, what are you getting? N square h square by 8ml square. Yes, beautifully. So this is the generic formula. You can have different quantum numbers, nx square, ny square, nz square, and you will have a generalized formula that exists. And lx square, ly square, lz square as well. If they are equal, you can put them as nx square plus ny square plus nz square into h square by 8ml square, right? And generalized form is n square h square by 8ml square. Beautiful. Right. And we know what psi is also, right? So now what does this explain? This is explaining me the energy when I have 3 set of quantum numbers. This is explaining me the energy when I have 3 set of quantum numbers. How does the wave function actually look like? That is what it is implying me. Yes. So in this case, this is the wave function with respect to x. This is the wave function with respect to x. So what happens here? When you put, right? When you put n is equal to what? N is equal to when you put 1. In that case, the energy becomes n square h square by 8 ml square. So it will be just h square by 8 ml square. Right? You will have a simple wave like this. You will have a simple wave like this. Yes. And what was the a in all these cases? Root of 2 over L. All that is fine. Right? When x equals 0, that was the case we observed. Right? Now, when you have two things, right? When n is equal to two quantum states, so you will have a nice thing like this. And when n is equal to 3, you will have something like this. Yes. So essentially, you are seeing the wave as well, and you're seeing the energy as well. N square, h square, by 8 ml square. How does the psi star look like? If this is psi, this is the wave itself, then how will psi star look like? Just the modulus of it, right? With a broader range, but yeah, modulus of it. This is how it looks like, right? Same thing with the modulus of everything below will come above. That's it. That is I star versus X graph. Yes. So you should know all this for sure. All these are important. Time dependent, time independent, all that we covered. And then you can practice all this. Just the same formula application now. You just apply limits there. Size I star, you put it, apply limits and get the value. Okay. Let me know if you have queries here. For now, I'm skipping it. Yeah. Free electron theory. All this is not so much to worry upon. Just know what it is. Okay. Simple theory. Just know the postulates, right? Energy levels are discrete. They're not continuous. They obey Pauli's exclusion principle. They obey Fermi-Dirac statistics. Again, all these guys. One guy will say an electron cannot have all set of 4 quantum numbers, right? Another guy will say you will always have 2 spins, right, and all that. Okay. And then all the other guys, right? So just the basic principle of principal quantum numbers and electron states. Yes. And these are all free electrons. Free electrons move a uniform potential. Free and independent electron approximation, leave it. N is replaced by N effective, leave it. Just few theory, just know that. Yes. And this is there. Yeah. Periodic potential, electron interaction exists. Just few things. Chumma look it up. Look at it. Okay. Fermi Dirac and then density of states, and we are done. Okay. So Fermi Dirac, what happens here? Fermi Dirac tells you the probability of occurrence of an electron having an energy of E. That's it. The probability that an electron has an energy of E. Okay. So f of E function is given by the formula 1 by 1 plus E power E minus EF by KT. See, when I want to compare something, I always need a relative term. And the relative term here is Fermi energy level. Okay. Fermi energy level, we'll define it only from here. Okay. So don't worry. It's a relative term. So 1 by 1 plus E power E minus EF by KT. K being Boltzmann constant, T being temperature. Yes. E being the energy that we are looking for the probability. Right? Beautiful. So let's take different cases and understand what happens here. Yes. Are you on the same page, guys? Can someone please quickly react? Yes. Thank you so much. Once again, guys. Yeah. So when E is greater than EF, what happens? So end of the day, I'm assuming absolute zero temperature. Absolute zero temperature, now this T guy becomes zero. If this T guy becomes zero, either it could be E power infinity or E power minus infinity. So if E is greater than infinity, it will be, E is greater than EF, it will be E power infinity. When E is less than EF, then it will be E power minus infinity. And that makes a big difference, right? So if E is greater than EF, E power infinity is essentially infinity. So infinity plus 1 is infinity. So 1 by infinity becomes 0. So essentially, what does it mean? At absolute zero temperature, if you go above the Fermi energy level, what is the probability of seeing an electron? Literally 0. Okay, fine. Next step. What if E is less than EF, right? When E is less than EF, this whole term becomes E power minus infinity. E power minus infinity is what? 0. So in that case, 1 by 1 plus 0 will be just 1. What does this imply? At absolute zero temperature, go below your Fermi energy level, probability of finding an electron is 1. Electron கண்டிப்பா இருக்கும்பா அப்படின்னு கான்ஃபிடென்ட்டா சொல்றாப்ல Fermi. Okay? Yes. Okay, fine. You yourself assume temperature is zero, right? What if temperature is non-zero? And there is a thing why I do this, right? If temperature is zero and E is equal to EF, it will be undefined. It will be indeterminate. Yes. So let's assume E is EF, right? But T is non-zero, right? Basically, non-zero meaning T is greater than 0 Kelvin. So in that case, what happens? T is non-zero, but the numerator is 0. So in that case, 0 by a non-zero quantity would be 0 only. So E power 0 would be 1. So 1 by 1 plus 1, 1 by 2. So in that case, when the energy is exactly equal to Fermi energy level, then the probability of occurrence of the electron is what? Half. Okay. So all these concepts, very nice concepts. Just know that. Okay. And then density of states will come. Density of states will come. And just simple problems, nothing much. Yes, they've given you temperature, they've given you the difference between E and EF. So you direct substitution to find the Fermi function. Using the Fermi function, evaluate the temperature at which 1% probability that it has an energy above 0.5. They have not directly given, they have just told that there is 1% probability that the energy, full question, that an electron in a solid will have an energy above 0.5, meaning what? Above this particular EF, the energy that I have, the probability that I have is 1%. The probability essentially is Fermi function, and the Fermi function is just 1%, which is 0.01. And above of 5 electron volt just means that the difference is 5 electron volts. Difference between whom and whom? The Fermi energy level and the Fermi function or energy that I'm looking for. Yes. So that is 0.5. And you direct substitution now, right? 0.5 electron volt E minus EF is given. F of E is given. K, you just have to find the temperature. Yes. So revising it all, Fermi function is 1 by 1 plus E power EF minus E minus EF by KT. Just remember this to find the number density of electron having in the interval E and E plus DE. In the interval E and E plus DE, the number density of electrons present there is nothing but 1 second, guys. 1 second. Just give me a second. All right. Yeah. So to find that the number density of electrons in that interval E and E plus E, right? So if you want to find the number density, what do I mean? I want to say how much electrons are present per volume, right? In that case, if I just know how much ever things that can occupy it, how much ever things that can occupy, how do you specify how much ever things that can occupy? Density of states. How much ever things that can occupy? Density of states multiplied by what is the probability that the occurrence of that state is an electron? What is the probability that the occurrence of that state is an electron? What is this? This probability is essentially f of e. This is density of states, that is g of e, right? And you're looking between the intervals e1 e2 here. Yes. So finding the number density is essentially taking the integral from e1 to e2, density of states multiplied by Fermi function, which we'll be using in semiconductors as well. So just know that. So I think we are only left with density of states. So if you have any queries till this point, just tell me. We'll proceed with density of states from here. Are we clear? Are we on the same page? Quick reaction. Yeah, thank you. Thank you. Thank you. Okay. Okay. All right. So moving on. Yes. Um, yes. What do I essentially mean? Density of states? The amount of states or the number of levels that can occupy between the energy E and E plus D. That is what I wanted, right? Now the number of levels that can be occupied between E and E plus D, right? Essentially, if I want to say E corresponds to N, E plus D corresponds to N plus Dn. That is the quantum number that I'm looking for. N essentially is contributed by both Nx, all the three Nx, Ny, and Z. For now, let's keep it N. Yes. So I just want to find the number of levels between whom? Between E and E plus D. Yes. Essentially, assume that this is represented by a naive sphere, right? This is represented by a naive sphere. That is how they have conventionally derived the density of states, right? Now, if I want to find the number of levels between N and N plus Dn, I just want to take the volume of the outer sphere, which is N plus Dn radius of a sphere, and N radius of a sphere. Yes. What is the volume of a sphere? 4 pi r cube. 4 by 3 pi r cube. Yes. So in this case, the radius of the first cube is n plus dn the whole cube. And the radius of the inner one is n cube. So 4 pi r cube by 3, right? 4 by 3 pi r cube. Right? Fine. So in this case, if you observe, if you take the cube of this, it will give you n cube plus dn cube plus 3n square dn plus 3n dn square. The higher powers of dn square and all, dn cube and all, you can remove it. So you'll essentially get just this term, and n cube will also get cancelled. You'll only get this 4 pi n square dn. Yes, beautiful. Now I have this. Still, I'm not satisfied. See, understand, you are not going to accompany for negative values of principal quantum number. By definition, principal quantum numbers only have positive values. In that case, a full sphere is not justifiable. A full sphere accounts for 8 octants, right? So what you lose, you only consider all nx, ny, nz being positive. So you literally have to account for only 1/8 of this volume, 1/8 of the value which you have found, right? So 1/8 of 4 pi n square dn. That will give you what? Pi n square dn by 2. Okay, fine. We got pi n square dn by 2. That is the number of levels. Beautiful. Again, is this meaningful? Not yet, right? I will not say n is meaningful. Yes. If I have E in my term, I'll say meaningful somehow. Energy, something I want. Yes. So what I'll do? I'll take from the same thing. We took K learn E we took. But E learn N we are going to take. Okay. So what was E? E was N square H square by 8 ml square. So in that case, what is N? So N square would be 8m L square E by H square. So in that case, so this is what N square is. And why am I also taking N? For simplicity? Because I want N square dn. So what I do is pi into N square dn can be put into N into N dn. N into N dn. I know very well N is just root of the whole thing which I derived, this root. Yes. What is N dn? N dn is just 2 and, N square root differentiation. That's it. N square differentiation. In this case, N square differentiation would be what? 2n dn is equal to, all these guys are constant, E will become dE. Okay. So yeah, I got, this is 2 n dn. So just divided by 2. So you'll get n dn. So you got n dn, you got n. So just multiply both, you'll get your answer, right? So n square dn is equal to n into n dn. N was this, n So sorry guys, some technical glitch. Yeah, is the screen visible? I think it is. Yes. Am I clear? Quick reaction, please. Is the screen visible and am I clear? Guys, okay, thank you so much. Yes. So we were at this place, right? So we were doing n square and n and NDN. So we got that. We multiplied them. Yes. So when you multiplied them, you got what? You got root of 8 ml square by h square e into 8 ml square by 2h square dA. You will not get satisfied. No, being a mathematician, it does not look good. So you take out the common terms, right? What is common here? This guy does not have 2 here. This guy has 2 here. Yes. So what I'll do instead is I just take that 1 by 2 outside. So this guy will become 8 ml square by h square whole power 1. This becomes 8 ml square by h square whole power 1 by 2. So it will become eventually 1 plus 1 by 2, 3 by 2. So 8 ml square by h square whole power 3 by 2, 1 by 2 root TD. Beautiful. Yes. We got this. Are we satisfied? We are not. Okay, we are not satisfied with this still. Okay, because there are terms that I can still reduce. You can see here, right? L square is there. L square and 3 by 2, 2 will cancel off and L cube will come outside. Same H square. If you take power 3 by 2, they'll cancel out and H cube will come outside. Yes. And 8 also, I can separate them as 2 and 2 square. So that 2 square will come out as 2 cube outside. Yes, only 2 will remain inside. Okay, so I'm just doing that process here. So I'm going to take uh, so it was what this was just n square dn. So what you want is pi by 2 n square dn. So pi by 2 multiply with this formula, right? Pi by 2 is there, 1 by 2 is there, 2 square 2 cube will come out, h square will come out as h cube. Already this becomes pi by 4, and m will be there already. M will be there, and this 2 will also be there under power 2 3 by 2. L square will come out as L cube, and root e will be root e only. That's it. So the final formula that you should remember is not this also. Don't worry, not this also. What you have is the number of levels only. Okay, but you are going to calculate density. Density is per unit volume, right? You have to divide by per unit volume, right? So in this case, the number of levels between E and E plus D in unit volume of the material will be just divided by L cube. Divided by L cube. Okay, va? So you just divide this by L cube, you will get this formula. Are we satisfied? We are still not satisfied. We missed one point, that every electron has 2 states, right? There are 2 levels possible for an electron. So in that case, we have to account for the 2 spin states as well. So you multiply this by 4, and the final formula you get is 4 pi by h cube 2 m power 3 by 2 root ED. And you must remember this. We'll be using this in semiconductors. Okay. So 4 pi by h cube 2 m power 3 by 2 root ED. Remember this. Tell this to yourself some 10 times and you will remember this, because that is what I did. Yeah. So that is what G of E. I told you the concept of number density, right? So density multiplied by the probability of the occurrence of an electron in that energy interval will be f of EDE. So you just take the integral of it. Yes. You can very well see it, the graphical representation of f of E and all, right? When t is equal to 0, right? If it was less than EF, you observe that the probability was 1. If it is greater than EF, you observe that the probability is 0. If it is somewhere in between, it was 1 by 2. And if the temperature is non-zero, you observe some nice curve like this, curvy curve. Okay. All these, if you want, you can remember. Okay. This is just simple electron density at 0 Kelvin. Okay. So what happens here? Electron density na number density of electrons they're asking. Number density of electrons they're asking na just density of states multiplied by Fermi energy level. Okay. Now they're only asking at 0 Kelvin. Okay. And we very well know for metals, 0 Kelvin, all the levels up to EF is occupied for sure. They are not semiconductors. Yes, they are conductors. So in that case, f of e will be 1, right, up to EF. So in that case, you just substitute as 1. You very well know g of e. It is 4 pi by h cube 2 1 by 3 by 2 root e d, right? Just root e will be there inside. Just take the integral and take the limits. That's it. Okay, they're just generalizing it. If you want, you can know. They're just putting some constants and making it weirder. But yeah, if you want, you can always take that. Okay. Average energy of electrons in metals is going to be what? Energy of the electrons multiplied by the volume in a material. And in turn, how will you find it? You find it by taking the entire g of e d, the g of e d, that will give you g of e into f of e will give you what? It will give you the density of states, number density of states, right? Number density of states. But what you want instead is the average energy of electrons per unit volume, right? And that will be what? Total energy of all the electrons per unit volume in states up to EF, and this in states up to EF because metals at 0 Kelvin. So Fermi energy level is 1, same case, right? Divided by total number of electrons. Average energy na all electrons is what is the total energy divided by total number of electrons. That is what you do. Okay. And that's the revision here. Okay. If you want, you can remember this constant. If you want, if you don't want, you have your calculator with you. Okay. Yeah, I think that's the end. If you want, you can remember these. All these guys. All these guys are derived guys. If you want, you can remember. Okay. And all these things are not there. Okay. And there are good enough problems here. If you want, you can see these problems. Okay. I'll send. I think it should be there in the zip file I sent. Okay. It's the same file as the zip file. Okay. That's it, guys. So, do you have any queries in quantum physics? Just quickly brushing up quantum physics. What did you learn? You learned about different models of expressing properties in physics. You express properties, few properties obey classical physics, few properties obey quantum physics, and you are not able to distinguish universal nature. Yes. So in that case, you define the exclusive parameters for each physics. We have always learned about classical physics, so we dive into quantum physics in this unit. Next, we learned about the drawbacks of classical physics that has UV catastrophe, that has problems with finding Wien's displacement and all that, that has problems in finding the universal expression for energy density and all that. So Mr. Planck came up with his formula, right? That formula, right? 8 pi nu square by c cube into e power h nu by kt minus 1, something like that. Yeah, 1 by e power h nu by kt minus 1. Yes, that formula. Yes. And then we observed that it was true for lower wavelengths and upper wavelengths as well. And then we saw the dual nature of waves, that it has particle nature as well. It has wave nature as well, dual nature of matter in itself. Right. There would be one beautiful diagram in which and no one told me that I was going to work with her. Particle and wave வச்சு ஒரு Schrodinger வச்சு ஒரு diagram இருக்கும் அந்த slideல. Okay. I love that. No one told me that I was going to work with her. Yeah. So that one. அதுக்கப்புறம் வந்து we learned about wave functions, right? Heisenberg's uncertain principle, de Broglie's wavelength, and all that we covered. Yeah, that's fine. So wave function, we learned about wave function on the basics. Wave function properties, physical significance being very important. It has to be finite, single valued, continuous, should have derivatives, we should be square integrable and all that. You should be able to test it. You should be able to know the problems in it. You should definitely. And then you should we learned about time dependence Cronenberg's equation, in which time independent case we derive the equation like minus h cross square by 2m dou square psi by dou x square plus b psi is equal to e psi. And time dependent case we also took care of the notation that we have to account for energy as well, time as well, right? So in that case, we express total energy in terms of time by differentiating with respect to t, and we got I h cross dou psi by dou t. So in turn, the whole formula became what? Minus h cross square by 2m dou psi by dou t, where psi depends on x and t, plus b depends on x and t, into psi depends on x and t is equal to I h cross square by I h square into dou psi by dou t, where psi depends on x and t. Okay, done. And then we learned about these discrete concepts, right? So we had one good flow. that starts from time dependence Schrödinger's equation, time independence Schrödinger's equation, and how I'll apply it. Then we went to application, that is one-dimensional potential well, where we had an electron dropped, and how do you find the wave function for it, where we first started with finding from the time independence Schrödinger's case, we put the potential 0, find the general form of equation by putting dou square psi by dou square plus k square psi is equal to 0, k square being assumed as 2me by h cross square. And then we saved it for future. And then we assume that psi was a sin kx plus b cos kx, and we assume x when x is 0, what psi is 0, when x is L, psi is L, psi is 0. So we substituted all that, and we got what? We got psi is equal to n sine, and we also used this parenthetical property, and where we got the a as the constant, which is root of 2 over L. The final formula became root of 2 over L sine n pi x by L. Yes. Now, from this formula, we derived it psi x, psi y, psi z when you have 3 coordinates and all that. And from the initial formula of k square, where k value we got as n pi by L, from there we derived energy was n square h square by 8ml square. So from that region also, we observed that energy can be having these. We forgot this concept, right? Thanks, actually. So n square h square by 8ml square. When we can have different configurations of quantum numbers is a very important concept. Yes. When even you have different configuration of quantum numbers that represent different states, you can have same energy is proved by that formula, right? Which formula? For example, nx square plus ny square plus nz square into h square by 8ml square. You can put 1 to 1, 2 1 1, 1 1 2. It will still give you what? 2 square plus 1 square plus 1 square, that is 6ml square by 6h square by 8ml square, right? So in turn, it is going to give me the same energy for different configuration of states. So I call them degenerate states. Okay, degenerate states, you should know the diagrams and all that, everything. I showed you psi versus x and psi square versus s as well. You should know that. And energy formula, energy application, all that is important. And then we moved on to density of states derivation, where we first started with finding the number of levels between E and E plus D, n plus n, n plus dn. And then we subtracted the quantities. And then we observed that it came to be pi n square by n square dn by 2. And then we took n and n dn. We took n was not a meaningful quantity, so we took it from E, where E was n square h square by 8ml square. So in turn, we found the expression for n in terms of E, and we substituted it. We took the derivative for finding the n dn, right? And then we used the spin state logic and multiplied by 2. And eventually, in beginning also, we reduced it to 1 octant by dividing by 8 also. Don't forget that. So final formula, you will get it as 2 ohm h cross square by 2 ohm. I forgot. 1 sec, wait. It should be 2 ohm power 3 by 2 root ED. I forgot the initial term. Yes. Yeah, 2 ohm power 3 by 2. Yes. So we had 4 pi by h cube, 2 ohm power 3 by 2 root ED. Yes. So that we had. And then we proved density of states into Fermi function. If you integrate in that energy level, energy interval, you will get the number density of that entity, number density of electron, right? And then we also observed that Fermi function is the probability of occurrence of an electron having energy E, where we derive 1 by 1 plus E power E minus E by KT and looked upon different cases. Yes. And finally, we substituted the formulas in finding number density, and few problems you have to practice yourself and get yourself clear. And that is the end of quantum physics. Are you all fine? Are you all with me on this? If everything is clear, just give me a quick thumbs up. Yes. Okay. Thank you so much. Yeah. Yeah. That's it. So, do you want a quick break, or shall I complete intrinsic and I'll go? Up to you guys.
Break.
Sorry?
Up to around.
One sec. Tell me now.
சாப்பிட்டு வரணும்.
Okay, pa. சாப்பிட்டு வாங்க. Okay. When shall we start? We started 8:15.
Yes. Okay.
Okay, pa. Intrinsic ரொம்ப சின்னதான், அவ்வளவு டைம் எடுக்காது. I'll take 20 minutes தான். இது நான் கொஞ்சம் பெருசா எடுத்துட்டேன்னு தோணுது. ஓகே ஓகே பீப்புள், வில் மீட் அட் 8:15. எல்லாம் புரிஞ்சுல?